Recall that the first data structure we discussed is array, and it is the simplest of all data structures. The second is stack. Stack is a structure which is an ordered collection of items or elements into which new items or elements may be inserted and from which items may be deleted at one end only. And we call this one open end as the top end. Say this one here is a stack. Now notice that there are two ends, the top end and the bottom end. For stack, it says that there is only one open end and we call it the top end. So this one, the top end, is the only open end, while the bottom end is closed. And so since this is the only open end, this is the end into which you can insert new items or elements. It is also from this end that you can delete or remove existing items or elements. Now, there are two common operations in all data structures: insert and delete, or the insertion and the deletion operations. For data structure stack, the insert operation is called push and the delete operation is called pop. So as you can see here, these two are the common operations for all data structures. Push is to add or insert a new element into the stack, and it is into the top end that you are going to insert or add new elements or new items. And when you implement this operation push, you implement it as a method or a function that accepts one parameter, and that one parameter is the new element that is going to be added or inserted into the structure stack. For deletion or delete operation, we call that pop. Pop will remove or delete the top element from the structure stack. And take note that you remove or delete the top element, not any other element. It is only the top element that you can remove. Why is that so? Because as I have mentioned a while ago, there is only one end that is open. And in that one end, you perform the push or the adding or the insertion of new elements, and you perform also the pop or the deletion or removal of existing items or elements. Now, examples to this structure are, we can cite several examples. One of that is pile of trays. If you go to a cafeteria or a fast food, you can find there pile of trays, right? So you have these trays, and this is the bottom tray and the topmost tray. So when you are going to get a tray, you normally get the top tray, right? The one at the top. You don't get the tray at the middle part. Worst, you don't get the tray at the bottom. You always normally, by default, remove the top tray. Okay, so that is the pop method or the pop operation. You remove the top element from the stack. And when you insert or add a new tray, you place it also on top. So you remove the top tray, you place new trays on top. Now the same is true for pile of plates. Okay, think of this as plates. So the same is true. When you remove a plate or you get a plate, then you have to remove by default the top plate, not the middle plate, or worst, you don't get the bottom plate. The same is true for pile of books, if these are books. And the same is true for pile of chairs, okay? So we have here the bottom chair, another chair, and then another chair. And then say this is the top chair. when you get a chair, you normally by default remove or get the top chair, not the middle chair, and of course, not the bottom chair. When you add more chairs into that stack of chairs or pile of chairs, you add on top, okay? You don't get the top and then put or insert those new chairs in the middle, okay? So it is always at the top end that you perform insertion, which we call as push, and you also perform the pop, which is the delete operation. Say, for example, you're going to perform this series of operations. Say, first operation is push A, and then say next is push B, third is pop, and then fourth is push C, and then fifth is push D, and the sixth is pop. Say you perform the first one, and say this is our stack push A. So you push A, it goes to the bottom, so that's where your A is. And the next push B, so you push a new element B, so B now is on top of A, and then you pop, so this is removed, and the next push element C, C is now on top of A, and next is push D, so D is on top of C, and then lastly pop, so D is removed. So what remains in the stack is A and C, right? So notice that the last element to get inside is the first element to get out. So if we push A, B, C, D, E in that order, this is the first, second to push, and then third, fourth, and the fifth, and the last element to be inserted or pushed into the stack. So it would look like this: A, B, C, D, and lastly E. So notice that the last element E to get inside is the first element to get out. So this structure stack is called last in, first out structure. So it is a last in, first out structure. The last element to get inside is the first element to get out. Now, aside from these two common operations, to insert is to push, to delete is to pop, there are also other operations, but these two are the two common operations present in all data structures. The first application that we're going to discuss for data structure stack is on the problem of determining whether or not an arithmetic expression with parentheses is valid or invalid. And how do we check if an arithmetic expression is valid or invalid? By determining if it has balanced parentheses, meaning that the number of left parentheses is equal to the number of right parentheses. Now, we have this term, parentheses count, which is equal to at any point in the arithmetic expression with parentheses, it is the number of left parentheses symbols encountered minus the number of right parentheses symbols encountered. So at any point in the arithmetic expression from the leftmost symbol to the rightmost symbol or to the end of the expression, we can determine the parentheses count. And there are two requirements for a valid arithmetic expressions with parentheses. First, that at any point in the expression, the parentheses count is greater or equal to 0, meaning it should never be negative or it should be positive or 0. The second requirement is that the parenthesis count is 0 at the end of the expression. Say for example, we have this arithmetic expression. This is the beginning of the arithmetic expression, the leftmost symbol, and this is the rightmost symbol. So as we scan the arithmetic expression from the leftmost symbol to the rightmost symbol, symbol by symbol, we are going to determine the parenthesis count at every symbol. And what is that value? It is, as stated above, it is the number of left parentheses, this one, minus the number of right parentheses encountered as you move from, or as you scan it from left to right. So at this point, the leftmost character, what is the parenthesis count value? Number of left minus number of right. So number of left is 1 minus, at that point, you have not encountered any right parentheses yet. So this is 0. So parenthesis count is 1. So this is 1. At this point, it is also 1. We have encountered 1 left parenthesis minus 0 right parenthesis. And this is also 1, 1. At this point, it is 1 minus 1. So this is 0. We have encountered 1 left parenthesis minus, we have encountered 1 right parenthesis at this point. So it is 0. At this point, we have encountered 1 left and 1 right, so it is 0. At this point, we have encountered 1, 2 left parenthesis minus 1 right parenthesis, so the answer is 1. Okay, parenthesis count is equal to 1. And this is also in here, parenthesis count is 1, 1, 1. And in here, it is 0. Why 0? Because at this point, you have encountered 1, 2 left parentheses, and you have encountered 1, 2 right parentheses. So the answer here is 0. Now, based on the values of the parenthesis count at any point from that up to the end, okay, checking for the first requirement, which is this, is the parenthesis count greater or equal to 0 at any point in the expression? At any point in the expression, take note that the value of the parenthesis count is greater or equal to 0. So it passed the first requirement. Second requirement is when we reach the end of the expression, the parenthesis count at the end is 0. Now, notice that at the end of the expression, the parenthesis count is equal to 0. So, the second requirement is also satisfied. So, since these two requirements, A and B, are satisfied, then we conclude, okay, therefore, arithmetic expression is valid because the two requirements are satisfied. How about for the second example? So what is the parenthesis count from the leftmost character to the rightmost character, which is E? So at this point, we have encountered 1 left parenthesis minus we have not encountered any right parenthesis yet. So this is equal to 1. 1 left minus 0 right is 1. At this point, we have encountered 2 left parentheses and we have not encountered right parentheses yet. So this is equal to 2 minus 0 is 2. And this is also at this point it is 2. At this point it is 2. At this point it is 2. At this point we have encountered 2 left parentheses, and at this point we have encountered 1 right parenthesis. So 2 minus 1 is 1. And this is also, parenthesis count is 1. At this point, how many left parentheses we have encountered? We have 1, 2, and 3. 3 minus how many right parentheses we have encountered at this point? It is only 1, this one. So minus 1. So the answer is 2. And this is also 2, 2, 2. And in here, we have encountered at this point, we have encountered 1, 2, 3 left parentheses minus, we have encountered 1, 2 right parentheses. So 3 minus 2 is 1. And this is also 1, and this is also 1. At the end of the expression, the value of the parenthesis count is 1. So let's check the two requirements. First requirement, that the parenthesis count at any point in the expression is greater or equal to 0. Okay, so from the leftmost character or symbol to the rightmost, at every point, the parenthesis count is greater or equal to 0. So this first requirement is satisfied. The second requirement is that parenthesis count must be equal to 0 at the end. But as you can see here, at the end, it is equal to 1, right? So PC is equal to 1 at the end and not 0. Therefore, this is not satisfied, the second requirement. So we conclude that the arithmetic expression is invalid because it does not satisfy the second requirement, which is that the parenthesis count at the end of the expression must be equal to 0. Meaning, when the parenthesis count is equal to 0 at the end, it means that in the arithmetic expression, the number of left parentheses is equal to the number of right parentheses. How about the third example? This is the leftmost character and this is the rightmost character. What is the parenthesis count at every point? Starting from the leftmost character, it is 0, right? This is 0 because at this point, we have not encountered any left or right parentheses. At this point, we have not encountered left and right parentheses. At this point, we have encountered 1 left. So this is 1. And we have not encountered any right parentheses. So it is 1 minus 0. And this is also 1 minus 0. So 1, 1 minus 0, 1 minus 0 is 1. Now at this point, we have encountered 1 left minus we have encountered 1 right. So it is equal to 0. At this point, the number of left and right is balanced. At this point, what is the parenthesis count? At this point, we have encountered 1 left parenthesis and 2 right parentheses. So the parenthesis count is equal to negative 1. Okay, so this is negative 1 at this point. Now, even if we have not finished scanning the whole arithmetic expression, we are still somewhere in the middle. We have not reached yet the end of the arithmetic expression when the parenthesis count is equal to a negative value. Then we could stop scanning the arithmetic expression and then we can conclude that the arithmetic expression is invalid because which of the requirements is not satisfied, letter A or letter B? It is letter A, of course. Okay. The first requirement is that at any point while you scan the arithmetic expression, the parenthesis count should be non-negative, meaning it should be positive or 0. It should not be negative. But since parenthesis count at this point is negative 1, it does not satisfy the first requirement. And therefore, it is enough for us to conclude that the arithmetic expression is invalid because it did not satisfy the first requirement. So what does it imply when the parenthesis count is equal to 0, like in the case of the first example, this one? When the parenthesis count is equal to 0, just like in the first example here, it means that the number of left and right parentheses symbols are equal and thus this arithmetic expression has balanced parentheses. When the parenthesis count is greater or equal to 0, just like in the second example, it means that there are more left parenthesis symbols than the number of right parentheses. And so, the arithmetic expression is not valid because it doesn't have balanced parentheses. When the parenthesis count is less than 0, just like in the third example, when the parenthesis count is -1 at the end, it means that there are more right parenthesis symbols found in the expression than the number of left parentheses. And so, since the parentheses left and right is not balanced, then the arithmetic expression is invalid. So there are two cases when the arithmetic expression is invalid, and that is first, when the parenthesis count is greater 0, which means that there are more left parentheses symbols than right parentheses. And the second case is when the parenthesis count is less than 0 or negative value, which means that there are more right parenthesis symbols found than left parentheses. And there is only, of course, one case for valid expression, and that is when the parentheses left and right is balanced, meaning the number of left parentheses symbols is equal to the number of right parentheses symbols.